In the last why DL-based CDR video, we will show you why you need a DL-based CDR owing to its mitigations of multi-VCO coupling, pooling issues, high power dissipation, and large area of the PO-based CDR per channel. Other benefits of the DL-based CDR are providing input reference clock jitter filtering, no jitter accumulation, a more stable system, a low acquisition time, and no jitter peaking at the same time compared to the PO-based CDR. Fortunately, the Phase Interpolator PI-based CDR should provide similar benefit to the DL-based CDR and could even have more advantages. Before talking about the PI-based CDR, let's go through what the Phase Interpolator PI is. As we discussed in the DL-based CDR, the voltage control delay line VCDL is to provide a phase change through the clock delay controlled by the supply voltage. Similarly, the Phase Interpolator is to provide final multi-phase duration for a phase change, and it is also require the bitrate clock as its input. The only difference is that the VCDL only need a single phase input clock, but the PI may need multiple phase input clocks as the reference phases to generate the interpolated phase from any two selected phases based on the weighting. In this PI image, there are 8 phases as the PI's input reference clock. The input control code WI will select 2 input reference clocks, like the CK-in0 and CK-in1, to interpolate the required CK-out phases. Therefore, generating those multi-phase input clocks could be critical. What could we generate? Think about the PO or DL images for 5 seconds. Right, the multi-phase input clock can be generated either from a PO or a DL. If a multi-phase VCO is available in a PO, then the PI's input phase could come from the PO directly. If the PO's VCO only provides a single phase, then the multi-phase clocks can be generated from the DL loop. The generated multi-phase clocks are spaced evenly across 360 degrees through the delay log loop, and that would also meet the PI's input multi-phase requirements. After understanding the topology of the PI, we can dive into the PI-based CDR. The topology of the Phase Interpolator PI-based is like the DL-based CDR, except the VCDL is replaced by the PI. Also, the ergo charge pump and ergo loop filter could be replaced by a digital loop filter. The loop operation is to perform a phase comparison between the input data and the interpolated phases generated by the PI. The digital loop would then optimize select the interpolated phase to sample the input data optimally, and then achieve the minimum bit error. Looks like the PI-based CDR is not much different from the DL-based CDR. Why would we need a PI-based CDR? Think about the frequency offset images for 5 seconds. Bingo! The transmitter and the receiver in a series may have a frequency offset, and the PI's phase interpolator phase can rotate at the rate equal to the offset. So, the PI-based CDR can operate over a wide range of data rates with a certain allowable frequency offset between the TX and the RX, even in a source asynchronous SerDes system. In the design, we must make sure the CDR loop bandwidth remains sufficiently greater than the frequency offset, such that the frequency offset is tracked and the data is sampled properly. in addition to the frequency offset. What else could be the PI phase in CDR more beneficial than the DO-based CDR? Think about your digital images for 5 seconds. Correct. The PI-based CDR could be implemented as the all-digital CDR as shown here, which has all the advantages of the digital circuit. For example, all-digital CDR has large sensitivity to the process, supply, voltage, and temperature variations. Also, the all-digital CDR would have a much small area in the advanced process, and the design is easily ported between different processes. The design challenge or schedule would be much less than the analog CDR. But any disadvantage of the all-digital PI-based CDR? Think about the discrete image for 5 seconds. Bingo! The clock phases are discrete and depend on the resolution in digital. Under the frequency offset, if the phase rotation is in a large discrete step, real-time data might not be optimal to achieve the minimal BL rate, and the large discrete phase step could lead to a large cycle-to-cycle jitter of the service recovery clock. If a revised design with many finely spaced phases must be produced, that would have a complex layout, mismatch, and even lots of couplings in the routing. So, the finely spaced phases will lead to a higher power dissipation and large area to accommodate the issue due to the increased number of clock phases. What can we do? Think about the continuous VCO clock images for 5 seconds. Correct. To smooth out the discrete phase shift step is to swap the phase lag and VCO output connections. The discrete change in phase selection from the digital loop filter DLF in the CDR phase tracking loop can be smoothed out by the PO loop's analog loop filter and charge pump. The PO provides smooth frequency and phase drifting in the phase tracking loop. So, the revised PI-based CDR could still achieve the all-digital CDR benefits and have continuous phase adjustment. Unfortunately, the revised connection image shows you that every CDR loop may require a PO to fulfill the feature, which would not be able to support a multiple channel application with a single PO for the reference clock generation. So, it gives up all the benefits of a single clock source we discussed in the DO or PI-based CDR. You could choose which one you prefer. Depends on the trade-off of both topology of the PI-based CDR. After understanding all the PI-based CDR, let's go through the jitter peaking implications of the PI-based CDR. The benefit of no jitter peaking in a PI-based CDR will only exist if the loop latency is not significantly larger than the PI-based update period. In other words, if the latency of the PI-based CDR is too long, and the CDR cannot track the input phase rate jitter such that the gradient of the input jitter has already the opposite of the PI phase shift control signal. So, the jitter peaking is serious as the latency is longer, and we will talk about the latency image in detail later. Here are the summarized images of why you need a PI-based CDR. As the DO-based CDR with a single PO is shared in multiple channels, there are no multi-VCO coupling pooling issues, high power dissipation, and large area of the PO-based CDR per channel. In addition, the PI-based CDR also provides input reference clock's jitter filtering, no jitter accumulation, a more stable system, a low acquisition time, and no jitter peaking at the same time if the loop latency is little. Third, the PI-based CDR can operate over a wide range of data rate with a certain allowable frequency offset between the TX and the RX. Fourth, the PI-based CDR has all the advantages of a digital circuit, such as less PVT sensitivity, small area, less design challenge, and short project time. Lastly, the all-digital ability when using a PI-based CDR allows in-system testing of timing margin in the actual operating environment. Such system-level design for test DFT increase the SoC system reliability. On the other hand, the cost, power, performance, and testability benefits of using PI-based CDR are passed along in the form of low price, longer battery time, and improved reliability. The cost reduction, low power, and small area of the PI-based CDR improves jitter performance in high-speed SerDes link. Thanks for watching. Before you go, if you're benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.